Why is quantum Fourier transform hard to simulate? Have you ever wondered why the quantum Fourier transform is such a tough nut to crack when it comes to simulation? Let's break it down in a way that makes sense. The quantum Fourier transform, often abbreviated as QFT, is a key operation in quantum computing. It's essential for many quantum algorithms, but simulating it using classical computers is quite a challenge. One major reason is the exponential growth of the quantum state space. When you add more qubits, the number of possible states grows rapidly. For example, with just 10 qubits, you have over 1,000 states to consider. This means that simulating the QFT requires tracking complex amplitudes for all these states, which becomes unmanageable for classical computers. From the hardware side, implementing the QFT is also tricky. It involves a series of quantum gates that need to create precise phase relationships between qubits. These gates must be applied with high accuracy and coherence. However, current quantum devices, known as noisy intermediate-scale quantum devices, struggle to maintain this fidelity. As the number of qubits increases, the complexity of the circuit grows, making it more prone to errors and decoherence before the computation can even finish. Preparing the input states for the QFT adds another layer of difficulty. Efficiently encoding classical data into quantum superpositions often requires additional resources like quantum random access memory. This technology is still largely theoretical and not easy to implement in practice. When it comes to the output of the QFT, things get even more complicated. The result is a quantum state that cannot be fully observed. Measurement collapses this state into a single outcome, meaning you can't just read out the entire Fourier spectrum. Extracting useful information from the QFT requires careful algorithm design, as it often serves as a subroutine within larger quantum algorithms. The QFT plays a vital role in algorithms like Shor's algorithm for factoring, helping to identify periodicities in functions encoded on quantum states. However, the challenges in simulating and implementing the QFT limit the size and complexity of problems that current quantum computers can tackle. Classical simulation tools struggle to model these operations effectively beyond a small number of qubits. In summary, the difficulty in simulating the quantum Fourier transform stems from the exponential growth of the state space, the complexity of the quantum gate sequences, the challenges in preparing input states, and the limitations in extracting output information. These factors make the QFT a central yet demanding operation in the realm of quantum computing software and algorithms.